Okay, so now that we have introduced graphs and weighted graphs and directed graphs and did some preliminary problems, now we can get into the nitty-gritty. There are 4 more sections of this chapter. 3 of them are focused on weighted graphs, and one of them, what we're doing today, 15.2, graph theory for unweighted graphs, is, as the title suggests, focused on unweighted graphs. So everything we do in this section, the graphs have no weight. So any tables that we might have are automatically adjacency tables. Of course, we're going to go very quickly from adjacency tables to matrices. As I promised, there's a deep connection between graph theory and matrix theory. So first definition, 2 vertices are adjacent, which is the English term for next to each other, are adjacent, if they are directly connected by an edge, which seems very reasonable. If there's an edge that connects them, then they are adjacent. They're next to each other. Now, an element, capital A sub ij of an adjacency matrix, capital A, is the number of direct connections between vertex I and vertex J. And notice if it's a regular graph, non-directed graph, then we have to have symmetry across the main diagonal, that if this vertex is connected to that vertex, then it goes both ways. But if it's a directed graph, then the adjacency matrix does not have to be symmetric. So let's do an example. It says find the adjacency matrix for the 2 graphs shown. So here's a graph. We have vertex A, and here's vertex B, and here's vertex C, and we have connection A, B, C, and here's vertex D. So we want the adjacency matrix. So it's going to be a 4x4 matrix. Now, just like an adjacency table, in the first row, A, B, C, D, and columns A, B, C, D. In this case, there's no from to because it's not directed. So does A connect to A directly? No. Does A connect to B directly? Yes, once. Does A connect to C directly? Yes, once. How about A to D? No. We have to have symmetry along the main diagonal, so that one has to be a 1. B does not connect to B. B does connect to C, but not to D. We have to have symmetry along the main diagonal. We have to have symmetry along the main diagonal. C does not connect to C, but it does to D once. And then we have to have symmetry along the main diagonal, symmetry, symmetry, and D does not connect to D. So this is the adjacency matrix, and they don't give a symbol for it, although later in the book they use capital, not in the book, later in the section, they use capital M for adjacency matrices. So we'll call it M for now. So 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0. Very straightforward. But now let's make it a little more complicated. What I'm going to do is I'm going to copy this and add some stuff. So now A to B in that direction, C to B in that direction, D to C in that direction, C to A in that direction, but also A to C in that direction. So now we have a digraph, a directed graph. And what is the adjacency matrix now? Well, let's see, A does not go to A. A goes to B 1 time. A goes to C 1 time. A does not go to D. B does not go to A. B does not go to B. B does not go to C. B does not go to D. C goes to A once. C goes to B once, C does not go to itself, and C does not go to D. And D only goes to C one time. So we have this adjacency matrix, which is kind of close to the previous one, but got some zeros instead of ones in some places because some of the directions are only one-sided. Okay, now definition. Not example, definition. An edge from a vertex to itself, which we haven't seen yet, but an edge from a vertex to itself is called a loop. So a loop is an edge from a vertex to itself. Definition. If there are multiple edges, between two vertices, the graph is called a multigraph. Definition: a simple graph has no loops or multiple edges. Okay, so we like simple graphs. They're simple to work with. Let's do an example. Find the adjacency matrix of the following two graphs. So here's A, here's B, here's C with two connections. C goes there, C goes to D, and we also have that right there. Notice this is a non-directed graph. It is not a simple graph for two reasons. One, there's a loop by D, and there are multiple edges connecting A and C. So it is a multi-graph, and it has a loop. So what is the matrix? Let's take a look. A does not connect to A, but it does to B. It does to C twice, but does not connect to D. B connects to A, not to itself, to C, and not to D. C connects twice to A, once to B, not to itself, and once to D. And finally, D does not connect to A, does not connect to B, does not connect, oh, it does connect to C, and it connects to itself. So here's the convention that we make. You'll notice that there are, if you kind of zoom into the D dots, if you get really close to the D dots, it looks like this, right? We don't see the loop if you zoom in close enough. So if you zoom in really close to the D dot, it looks like that, which means it essentially has has degree 3, because there are 3 edges leading out of it. So in the column for D, it has to add to 3. So what we do is we actually consider D to connect to itself twice, because I can go this way or this way to connect to D. So loops have a double count. So this is the adjacency matrix for this graph with the convention that we just used. We might say, well, why do we have that convention? We'll see. We'll see. It makes sense in as we get a little further. So now let's do another one. Here's A, here's B in that direction. Here's C, and it goes in that direction. And then we have a loop in this direction, not a loop, but a path, an edge. And then we have an edge in this direction. And then here's D, and we have an edge in that direction. And we have an edge in that direction. So now we have a digraph. So let's take a look. A does not have any loops, so A does not go to A. A goes to B once. A goes to C once, and A does not go to D. B Yeah, B does not go anywhere. So zeros across the board for B. Now C goes to A twice, does not go to B, does not go to itself, and does not go to D. And then D does not go to A, does not go to B, goes to C once, and goes to D to itself once. You can't go in both directions because if you zoom in on D again, this one goes out, this one goes out, but this one, that one comes in. So you can only leave twice. Notice how, like before, the out degree is given by the row. To look at the D row, it adds to 2, but the in degree is given by the column. It adds to 1. Okay, so with those under our belt, let's jump into exercise 15C. Okay, question number 1. As always, your job, hopefully, is to pause and do each of these yourself and not just copy my answer. So find the adjacency matrices for the following graphs. Okay, so here's the graph for part A. It looks something like this. So go ahead and pause it and find the adjacency matrix. So it's a 4x4, A to B to C to D, B to A, not to itself, to C and to D. C just goes to B and D, so not A or itself. And D goes to A, B, and C, but not itself. Okay, that was easy. Part B. We're going to copy the graph. And we are going to make it into a directed graph by putting a direction here, a direction here, a direction here, a direction there, and a direction there. So go ahead and pause and come up with the adjacency matrix. So A does not go to itself, it goes to B, does not go to C, does not go to D. B only goes to D. C only goes to B. And D goes to A and to C, but not to B or itself. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. And then we have part C. So this one has A, B, E, and those are connected. And then we have down here D, those are connected. And then we have here C, and those are connected. So again, we have a regular graph. This one is 5x5. So go ahead, pause, go ahead and do it. So A does not go to A, goes to B, not to C, not to D, but it goes to E. B goes to A, not to itself, to C, to D, to E. C does not go to A, goes to B, does not go to itself, goes to D, does not go to E. D does not go to A, goes to B, goes to C, does not go to itself, goes to E. And E goes to A, to B, not to C, to D, and not to itself. And D, ooh, this one looks fun. So what do we have here? Here's A, here's B. We got a directed graph. Here's C. We got a loop at C. Here's D. Here's E. Here's F. Let's move that E over a little bit. And then we go to A in this direction and back in that direction. Okay, let's go ahead and make the 6x6 adjacency matrix. Okay, A does not go to itself, goes to B, doesn't come close to C or D, goes to E, but not to F. B only goes to C. C goes to D and to itself. once, but nothing else. D doesn't go anywhere. Only things go into D. D doesn't go anywhere. E goes to A and to F, and that's it. And F doesn't go anywhere. So you see, once you get the hang of these things, they're not that hard so far. Question 2. State the features of an adjacency matrix which tells you that the graph is simple. How can I tell by looking at the matrix whether the graph is simple? So think about that for just a second or two, and then pause it, come back. So no loops, which means nothing goes to itself. Well, how do I know if something goes to itself? You'd have to have a number along the main diagonal. So if there's only, no, not a number, but a non-zero number. So no non-zero numbers along main diagonal implies no loops. And what's the other thing that might make a graph not simple is to have a multi-graph, have multiple edges. So if there's more than one edge connecting two vertices, and for a directed graph, it would be in a certain direction. Did it just stop recording? Am I still recording? I'm still recording here, but okay, 1 second. I can still talk. If you have more than one connection between two of them, between two vertices, if it's a regular graph, you would see that with a non-zero number in any of the entry, not a non-zero, but a 2 or more in any entry would tell you that it is a non-directed, non-simple graph if there's 2 edges. And the same holds for a directed graph. So if there's anything other than a 0 or 1, then you automatically would not have a simple graph. So any number other than 0 or 1 implies that we have a multi-graph. So the answer to the question is you can't have anything other than 0s and 1s, and you have to have 0s along the main diagonal. Both of those would indicate that we have a simple graph. Question 3. Explain how you can use the adjacency matrix to find A, the degree of each vertex in an undirected graph. How do I find the degree of a vertex in an undirected graph? Well, you can add up. Because it's undirected, we're going to have symmetry, which means the row numbers will add up to the same as the column numbers. So you can add the numbers in that vertices, row or column. They'll give you the same number. B, how about the in degree? The in degree, add, we spoke about this before, so this is not new. Add the numbers in that vertices column. And the out degree, add the numbers in that vertices row. So that was not new. We've done that before. We spoke about that before. So now finally, the last question for the section, or for this exercise, question 4. The following adjacency matrix shows the relationships between a group of people where a 1 in the entry of row I, column J, indicates the person I knows the name of person J. So A sub ij equals 1 if and only if person or row I person, if, I guess we'll call it person I knows the name of person J. Now, this is certainly going to be a directed graph because, I know, a famous actor's name, but that famous actor is not going to know me. So just because you know a name in one direction, you don't automatically know it in the other. So here's the matrix. We have, normally I do columns. I don't know why I just decided to do it by row. I'm sorry, normally I do rows, but for some reason I did columns. We all do weird things sometimes. Okay, so this is the adjacency matrix. So who knows the most number of people just by looking? Person C, person 3, whatever, knows 4 people's names versus 3, 3, 3, and 2. So person C, hey, way to go. Anyways, A, part I. Explain why the matrix has a 1 in each entry on the leading diagonal, the main diagonal. Everyone knows their own name. Person I knows the name of person I. If you don't know your own name, maybe you have amnesia, but then you wouldn't know anyone else's name. I don't know. Let's not worry about those strange examples. Keep it simple. So person I knows their own name, okay, i.e. own name. Okay, and double I. Explain why the graph does not have to be symmetric. I already did this. It's possible, right? Possible for person I to know person J. What I mean by that is the name of person J, but not vice versa. Okay, part B. Without drawing the graph, find A, how many names A knows? 3. Just read the column. Sorry, just read the row. A knows 1, 2, and 5. 2, the number of people who know the name of C. Ooh, go to column C, 3. B, C, and D all know C. Who knows the most names? Ooh, that's C. And IV, whose name is known by the most, and that would be E. Not drawing any graph here. I can just read it from the matrix. And part C. State whether there's anyone who does not know A's name. Well, okay, who does not know A? C, D, and E don't know A. I mean by that A's name. So state whether there's anyone who does not know A's name and also does not know anyone who knows A's name. So C does not know A's name, but C knows B, who does know A's name. So not C. D does not know A's name, but D knows only C, D, and E, none of whom know A's name. So D does not know A's name, and D does not know anyone who knows A's name. And E does not know A's name and does not know anyone who knows A's name. So it looks like D and E are going to have a very difficult time figuring out A's name, because not only do they not know someone who knows A's name, but they also don't know a person who knows A's name. Now, this kind of alludes to the fact that if you want to figure out a way of getting from D to A in 2 steps, knowing someone who knows someone, what do you think we can do to the matrix M, which is the adjacency matrix, to determine whether or not someone can get to someone else in 2 steps? So perhaps you guessed it, we can raise it to a power. So let's throw in, let's do black. So let M be the adjacency matrix of a graph. The number of walks of length n from vertex I to vertex J is M sub I J or m to the nth power sub ij. In other words, it's the ijth entry of m to the n power. So if you want to figure out whether I can get from here to there in 7 steps, I will take my adjacency matrix and raise it to the 7th power and then look at that entry. But it doesn't just tell me whether I can or not. It actually tells me how many ways I can do that. So if there's 19 ways of getting from there to there in 2 steps, a 19 will pop up in that entry. This is just really cool stuff. Now, the number of walks of length are or less between vertex I and vertex J is, now unfortunately, this one has, at least at this level, no convenient way of doing this. What you have to do is look at the original matrix, square it, cube it, go all the way up to whatever number you want, and then look at the ij entry. So if I want 10 or fewer steps, I got to check how many in 1 step, that's m, how many in 2 steps, that's m squared, how many in 3 steps, that's m cubed, do them all individually, and then add them all together. Of course, this is the same as if I can either first add all the matrices and then check the entry that I'm looking for, or I can first do each one individually and then add them up together. I will get the same result. So with this under our belts, let's go ahead and do exercise 15D. Question 1. The adjacency matrices for the graphs in exercise 15C, question 1, 15, oh, I have it right here, are shown below. A, B, C, and D. So what we can do here is copy. That's my A. Oh, we can also see if we got it right or not. So here's part A. I get 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0. Yay, I got it right. Okay. We'll do each one separately. It says use these matrices to find the number of walks of length 3 between A and A. Number of walks of length 3 from A to A. How many ways can I get from A to A in 3 steps? Okay, well, do your thing. So I'm going to first edit a 4x4 matrix, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0. And then I'm going to take that matrix A to the 3rd power. And I look at A, or we'll call it matrix M. Matrix M cubed sub 1, 1 is equal to 2. So there are 2 walks of length 3. And just for fun, let's list them. All right, what are they? What are those? You can look back. What are they? So starting at A, and we go someone, and then we end at A. So we have A, B, D, A, or A, D, B, A. Cool. All right. Part, oh, they also wanted something else for part C. I'm sorry, for double I. They say the number of walks of length 3 from C to D. So number of walks of length 3 from C to D. So I go to the 3rd row, 4th column, and I look at M cubed 3, 4 there are 5 walks from C to D. I'm not going to ask you to write them out. All right, B. So now we're going to go back here. And let's duplicate this one. Okay, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0. Yeah, I got it right. Okay, so now we're going to edit a. Okay, so do it again. I'm going to edit another matrix 4 by 4. 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0. That's my matrix B to the 3rd power. So for part I, which is A to A, I get 1. And for part double I, which is C to D, the answer actually is 0. There are no walks of length 3 from C to D. For part B, if you look at B, C to D, I can get there in 2 steps, B, C, B, D, but I can't get there in 3. How do I get from A, B, D? Yeah, so cool, so cool. All right, C, this was a 5 by, how do I, there we go, 5 by 5 matrix. So I'm going to edit a new matrix. This one's going to be a 5 by 5. 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 0. Okay, this is what I'm calling matrix C. So matrix C to the 3rd power. I gives me 2, and double I, we're still doing CD, so that gives me 5. And finally, part D. This was a 6 by 6. Oh, this is a lot of work. But imagine having to do it by hands and making sure that you get them all and not missing any. That is not something I would relish doing. Okay, 6 by 6, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 1. Actually, you could just enter through the zeros. Okay, so this was matrix D to the 3rd power. And we have none. And we have 1. Okay, fun stuff. Okay, now question 2, it says, by considering an appropriate power of a matrix, verify your answer to exercise 15C, question 4, part CI. Oh my God, say that 10 times fast. So question 15C, question C, question 4, part CI. There is no part CI. So this is certainly a mistake. Let me check the errata page to see what they meant. So I'm gonna pause for a second while I do that. Okay, so yes, that is a mistake. And they just said take out the I. So question 4, part C. State whether there is anyone who does not know state whether there is anyone who does not know A's name and also does not know anyone who knows A's name. So first, let's copy the matrix for this problem, which is this one right here. Okay, whoops. Okay, so this is the matrix M. Okay, so this is the matrix of people who know someone else. Now, if I don't know someone who knows A's name, that means I can't get to A in 2 steps. So let's take a look at M squared. So make a new matrix. edit. This is a 5 by 5, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1. So this is what I'm calling matrix E. Matrix E squared. So M squared. And that gives me 2, 2, 1, 1, 2, 2, 3, 2, 1, 2, 1, 2, 3, 3, 3, 0, 1, 2, 3, 3, 0, 0, 1, 2, 2. So if I don't know someone who knows A's name in 2 steps, that means I can't get to A in 2 steps. Well, those zeros tell me that D and E cannot get to A in 2 steps. And of course, they also cannot get to A in 1 step. C couldn't get to A in 1 step, but C could get to A in 2 steps. So that does verify what I had to kind of really examine the matrix to figure out. This does it immediately, which is really, really nice. All right, question 3. It says, use the adjacency matrices M to answer the following questions. Okay, so here's part A. Here's my M. And the matrix is a 4 by 4, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0. So part I says, find M squared. No problem. That's just editing another matrix. We'll call this F. This is a 4 by 4 matrix. 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0. So this is matrix F, which I'm going to square. That gives me 2, 1, 1, 1, 1, 2, 1, 1, 1, 1, 3, 0, 1, 1, 0, 1. And it also wants M cubed. So the same matrix F, I'm going to raise to the 3rd power. 2, 3, 4, 1, 3, 2, 4, 1, 4, 4, 2, 3, 1, 1, 3, 0. So part 2. Write down the number of walks of length 2 from C to A. 1. Immediate. That one right there. C to A. 3rd row of 1st column. Length 2. Find the number of walks of length 3 or less between C and A. Well, I have 1 of length 1, 1 of length 2, and 4 of length 3. So that gives me a total of 6 walks of length 3 or less between C and A. Awesome. Now, we're throwing in a definition here. The diameter of a graph, definition, in the middle of the lesson. The diameter of a graph. What's the diameter of a circle? It's the distance from one edge to the other. In other words, if you look at all the points in a circle and you connect any 2 of them by a line segment, right? If I have a circle right here, if I connect those 2, or this one and this one, they're going to have some lengths, but nothing beats the length across the circle from one edge to the other. In other words, the diameter is the longest length that connects 2 points. So let's see how we extrapolate this term diameter to a graph. The diameter of a graph is the length of the maximum shortest walk between any 2 vertices. So all the vertices can be reached from any other vertex in a walk of length less than or equal to the diameter of the graph. What does that mean? Well, first let me write it. So the diameter of a graph is the length of the maximum shortest walk between any two vertices. So it said for part 4, use the powers of the adjacency matrix to find the diameters of each graph. Okay, because we're only working for part I right now. Okay, let's take a look at this one. I'll use a different color here. So, okay, so look at all the zeros. We don't get walks of length 1 in those entries. A to A, A to D, B to B, B to D, C to C, D to A, D to B, and D to D. So the diameter can't be 1 because we can't get from anywhere to anywhere else in one step. Now, this one takes care of that 0. 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 And this one, and this one, and this one take care of those zeros, which means if I consider 2 steps or less, I can get from any vertex to any other vertex. So the maximum shortest walk between any 2 vertices is 2. Therefore, the diameter of this graph is equal to 2. In 2 steps, I can get from anywhere to anywhere else. Let's do matrix, or let's do part B, which is the following adjacency matrix. This is a 5 by 5. 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, and 0, 0, 1, 1, 0. We got lots of zeros here. So part I, let's find m squared. So I'm going to go back to my calculator and I'm going to edit. We'll call this one G, 5 by 5. 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0. Okay, hopefully I did it correct. So let's just double check quick. That was pretty quick. Looks good. So that's G. So the matrix G squared is 1, 0, 1, 0, 0, 0, 2, 0, 1, 1, 1, 0, 3, 1, 1, 0, 1, 1, 2, 1, and 0, 1, 1, 1, 2. Meanwhile, matrix G to the 3rd power is 0, 2, 0, 1, 1, 2, 0, 4, 1, 1, 0, 4, 2, 4, 4, 1, 1, 4, 2, 3, 1, 1, 4, 3, 2. So let's take, okay, so let's go in order here. So that was part I, m squared and n cubed. Okay, so now part double I says, write down the number of walks of length 2 from C to A. There's 1. And that's this one right here, C to A. And then find the number of walks of length 3 or less between C and A. Well, 3 steps, 2 steps, 1 step. That's still 1. There's only 1 walk of length 3 or less between C or A. Okay. And now, what is the diameter of this matrix? So let's take a look. First, we have 0, 0, 0, 0, 0, 0, 0, all these zeros. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 zeros. That clears up 1, that clears up 1, but those are still zeros. That clears up that one, and that one, and that one, and that one, and that one. Still a 0, and that one, and that one. Still a 0, cleared up, cleared up. So we have 4 more to worry about. Cleared up, cleared up, cleared up, clear it up. So the diameter is 3. In 3 steps or less, I can get from any vertex to any other one. So the maximum shortest walk between any 2 vertices is 3. Diameter 3. And question 4. The following adjacency matrix shows the connections between some ports in the Shetland Islands off the coast of Scotland. The ferries go in both directions between each pair of ports. Castle Bay, Eigg, Lochboisdale, Laig, Rum, Tyree, and Tobermory. Castleberry, Eigg, Lochboisdale, Mallaig, Rum, Tyree, and let's think ahead. Let's put this down. Let's move this over. And Tobermory. And we have 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0. Oh, okay. Lots of zeros till the end is 1. And only Rum gets a 1. And the second and fourth get 1s. And the first and last will get 1s. And the first, the third, and the 6th. Okay, let's make sure I did that correctly. It looks like I did. Yeah, and it's symmetric. So this is a non-directed graph. Okay, so A. Find the number of routes you can travel to get from Lochboisdale to Castle Bay in 3 trips. No problem. The only problem is entering this in my calculator. This will be matrix A. Sorry, H is going to be a 1, 2, 3, 4, a 7 by 7 matrix. 0, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1. 4th row, 1, 0, 2, 3, 4, 5, 1. 1, 2, 3, 4, 1, 0, 0. 0, 1, 0, 1. 0, 0. Uh-oh. Uh-oh. Easy to make a mistake. I'm gonna do comment. Okay, 0, 0, 1, 1, 0. 1, 2, 3, 4. Yeah, 7, right? 0, 0, 1, 1. Oh, no wonder. 0. Okay. Okay. 0, 0, 1, 0, 0. Okay, that's good. And this one is not good, so let's fix that. And that should be a 0. Okay. And this one should be a 1 there. Okay. 4th row, that should be a 0, but that should be a 1. Okay. That should be a 0, but that should be a 1. Okay. First one and last one should be 1s. And finally, that one should be a 1. And that one should be a 0. Okay, woo, so that's matrix H. So, okay, matrix H to the 3rd power. Lochboisdale is 3rd row and Castleberry is 1st column. So the answer is, the matrix cubed 3, 1 is equal to 5. Part B. By considering the powers of the adjacency matrix, find which ports it is possible to get from Tyree using the ferry system. Okay, So if I'm getting to Tyree, sorry, from Tyree, I'm looking at the second to last row. So for M, I see I can already get from C and to TL, whatever those are, Castle Bay and Tobermory. If I do H squared, and I look at the, well, M squared, and I look at the second to last row, I can now add L and TI. Okay, if I go to M to the third power, and I look at the second to last row, I have the first, the third, CL, Tyree, and Tobermory, which I already have. If I do it to the fourth power, same ones. If I do it to the fifth power, same ones. I didn't prove that if I go to the 917th power, that it's never going to be anything else. But I just did the sixth one, and again, I get the same results, just these four. So I will conclude that it's highly likely that these are the only four that I can get to. So now it says an extra fairy root is now added between Maleg and Lochboisdale. So this one becomes a 1. Maleg and Lochboisdale. So by symmetry, those both become 1s. So it says write down the new adjacency matrix. Okay, so I'm going to duplicate this. And then I'm going to clean up a little bit. So those become 1s. Okay, that's the new adjacency matrix. And hence state the two ports that are furthest apart. Hence state the two ports that are furthest apart. Okay. Well, what would make two ports the furthest apart is it takes the longest until they're connected. So let's go ahead and go into my editing system for H first, and what I'm calling matrix H, and go to the third row, fourth entry, and make that a 1, and make that one a 1. So this is my new H. Okay. So we want the matrices that are furthest apart. So I guess we want the power of the matrix. Basically, we want the diameter of this graph. So I'm going to go ahead and square it. And I still have a bunch of zeros. So let's take a look. Okay, still have a 0. So what I'm going to do here is in black. So this is no longer a 0 after squaring. This is still that's no longer a 0. In the second row, whoops, in the second row, that's not a 0. That's not a 0. In the third row, that's not a 0. And neither are those two. In the fourth row, those aren't zeros. That's not a 0. And that's not a 0. In the fifth row, that's not a 0. That's not a 0. In the sixth row, that's not a 0, and that's not a 0. And in the seventh row, that's not a 0. Okay. So the rest of them are still zeros after doing 2. So now let's go to h, what I'm calling h to the third power. That's still a 0. And that's no longer a 0. That's still a 0. That's no longer a 0. But those are both still zeros. In the third row, that's no longer a 0. In the fourth row, that's no longer a 0. In the fifth row, that's no longer a 0, as is that. In the sixth row, that's not a 0. And in the last row, those aren't zeros. Okay, so now we do the fourth power. And let's see what we have. That's not a 0. 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 So 2 to go. Actually, by symmetry, those are the same 2. So E to TI. After 4 steps, they're still not connected. If I do this to the 5th power, now they're connected. So 5 steps to connect them. So the diameter of this graph is 5. Eig and Tyree are 5 away from each other. I'd actually like to make a picture of this, but they don't ask me to. They go, in fact, that's the end of it. That's the end of that problem. I'm going to make a picture of this. I want to see what's going on. I want to see if I can see why E and Tyree are 5 steps apart. So here's Castle Bay, which goes to Loch Boisdale and Tobermory. Eig, which is here, goes to Rum. Loch Boisdale goes to Castle Bay, which I already have, and Tobermory. Mallaig only goes to Rum. Rum goes to Eig and Mallaig. I have both of those. Tyree. Oh, I left that out for some reason. Castle Bay goes to Eig, also goes to Tyree. So let's go this way to Tyree. So Tyree goes to there and to Tobermory. And Tobermory goes to Castle Bay, goes to Loch Boisdale, and goes to Tyree. So this is kind of strange. How can E and TI connect at all? So let's do this again. Castle Bay has 3, TI, TO, and L. I have them all written down. Eig only goes to R. Loch Boisdale goes to Castle Bay and Tobermory. Mallaig and to Rum, I have that. Rum to Eig and Mallaig, I have that. Oh, of course, we added a route between Mallaig and Loch Boisdale. So this was added after the fact. Okay, which means now we can see it. E to R to M, 1, 2, 3, L, and then either C or TO and then TI. So it is in fact 5. Interesting how very easily seen from the graph itself, as opposed to from the matrix, right? The matrix is just numbers and not very visual. So sometimes I think it might be easier to do the matrix powers approach and do it that way. And sometimes it might be easier just to draw the graph. You have two options. In this case, it looks like drawing the graph was definitely the easiest way to see. Okay, question 5. Use the directed graph you drew for exercise 15B, question 5. 15B, question 5. Oh, wow. This was the fairy problem in the last section. To write down an adjacency matrix for the ferry connections on Lake Starnberg. Okay. Okay, so I don't have that. I don't know where it is. So let's try this again. So here's Starnberg. Starnberg goes to Polsenhofen. I'm doing ferry 1 first, which goes to Tutzing, which goes to Bernried, which goes to Seeshopt, which goes to Ambach, which goes to Ammerland, which cuts back across to Tutzing, which then goes directly to Starnberg. So that's the first one. Next one, Starnberg goes to Ammerland, which goes to Ambach, which goes to, no, that's horrible, try it again. Seeshopt, which goes to Bernried, which goes to Tutzing, which goes to Polsenhofen, which goes to Starnberg. And finally, Starnberg goes to Polsenhofen, which goes to Tutzing, which goes to Ammerland, which goes to Ambach, which goes to Seeshopt, which goes to Bernried, which goes to Tutzing, which goes to Polsenhofen, which then goes to Starnberg. Okay, so that was a directed graph. Now we want an adjacency matrix. So 1, 2, 3, 4. Okay, so okay, the matrix. That's Starnberg, Polsenhofen, Tutzing, Ammerland, Bernried, Ambach, and Seeshopt. 1, 2, 3, 4, 5, 6, 7. The same thing here. Starnberg, Polsenhofen, Tutzing, Ammerland, Bernried, keep them in order. Bach and Seeshopt. Okay, so there are no loops. So because there's no loops, I can immediately put zeros there. Now Starnberg, does it go to Polsenhofen? It goes twice to Polsenhofen. And does it go to Tutzing? Not directly. Does it go to Ammerland? Once, and does not go directly to anywhere else, okay? Meanwhile, Polsenhofen goes to Starnberg twice, goes to Tutzing twice, and doesn't go anywhere else. Tutzing goes to Starnberg once, goes to Polsenhofen twice, goes to Ammerland once, goes to Bernried once, but does not go directly to the others. Ammerland does not go to Starnberg, does not go to Polsenhofen, does go to Tutzing once, doesn't go to Bernried at all, goes to Ambach twice, and does not go to Seeshopt. Bernried does not go to Starnberg. It does not go to Polsenhofen. Bernried does go to Tutzing twice, does not go to Ammerland, does not go to Ambach, and it goes to Seeshopt twice. Ambach does not go to Starnberg, does not go to Postenhofen, does not go to Tutzing, does go to Amerland once, does not go to Bernried, and goes to Seeshopt twice. And meanwhile, Seeshopt does not go to Starnberg, does not go to Postenhofen, does not go to Tutzing, does not go to Amerland. It goes to Bernried twice. Oh, I think Bernried to Seeshopt I wrote 2, but it should be 1. Yeah, Bernried 1. And Seeshopt to Ambach is 1. Hope that's it. I'm running out of time for my next lesson, so went a little quickly. But that seems to be the directed matrix. By taking a suitable power of the adjacency matrix, well, let's go ahead then and throw this in. I'm going to call this matrix I. And this is a 1, 2, 3, 4, 7 by 7. 0, 2, 0, 1, 0, 0, 0, 2, 0, 2, 0, 2, 0, 0, 0, 0. 1, 2, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 2, 0, 0, 0, 2, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 2, 0, 0, 0, 0, 2, 1, 0. Okay. So by finding an appropriate power, well, let's square it. By taking a suitable power of the adjacency matrix, find all the pairs of towns that are not connected directly or with at most one stop, stating clearly the direction of the connection. Again, by taking a suitable power of the adjacency matrix, find all the pairs of towns that are not connected directly, so not directly connected directly. Okay, so let's take a look. I obviously don't care about any town with itself. Okay, we don't care about a ferry from a town to itself. That makes no sense. Now, Starnberg and Postenhofen, those are connected. Starnberg and Tutzing, I have one direction but not the other. Okay, so we want to find all pairs that are not connected directly or with at most, find all the pairs of towns that are not connected directly or with at most one stop. Not directly or with at most one stop. Why am I not understanding the question? Find all the pairs of towns that are not connected directly. Well, let's first find them, the ones that are not connected directly. So if we look at these numbers, these are the symmetric pairs. Okay, those are all the pairs. So not connected directly or with at most one stop. Okay, so going from top left. So the first one we have is Tutzing. Wait, what? Oh yeah, okay. So it looks like Tutzing to Starnberg has one And all the pairs of towns. Okay, I think that was a waste. All right, well, and most of that, what do they want here? Taking the suitable power of the matrix. Well, let's take a look at squared. Let's do m squared. 4, 0, 5, 0, 0, 2, 0, 2, 8, 0, 4, 2, 0, 0, 4, 2, 7, 1, 0, 2, 1, 1, 2, 0, 3, 1, 0, 4, 2, 4. This doesn't make any sense. I'm gonna beat this. 2, 4, 0, 2, 4, 1, 0, 0, 0, 1, 0, 4, 4, 0, and 0, 0, 4, 1, 0, 0, 4. All right. Find all the pairs of towns that are not connected directly or within most one stop. Okay. So in the first graph, Starnberg to Tutzing is connected directly. Starnberg to Bernried is not, but it is in the other direction. So Bernried to Starnberg does happen. It's got one stop. So again, Starnberg to Tutzing. So Tutzing goes to Starnberg in one step. Running out of time. All right, I'm going to pause this and teach my class and then come back and finish it. So I'll be back soon. So I was thinking about this a little bit as I was working with my other lessons. And I'm pretty sure what they want is actually easier to establish if you look at the original graph. Because they're saying find all pairs of towns not connected directly or within most one stop. So what I'm seeing here is that if you look at the graph, Strasbourg is connected to Amherst or AMM, I think it's Amherst, whatever, and Ambach via one stop, Holstenhofen and Tutzing via one stop, which means Strasbourg to Bern, whatever, and Strasbourg to Schiesbout. There's no one direct connection or with one stop in between. That one requires, those each require at least two. Now from Polstenhofen, I can go up to ST and follow that to AMM, that's 2. I can go down to T and follow that to AMM, which I already know, or down to T and B, which means I can't get from P to Ambach in 2 steps, and I can't get the P to Schieshopt in 2 steps. Meanwhile, if I'm an AMM, let's see, I can get to Ambach and Schieshopt. I can get to Tutzing and Polstenhofen and Tutzing and Bernried, but the only thing I cannot get to in 2 steps from Amherst is ST. I cannot get to Starnberg, but I can get there the other way. So I can get there in one direction, but not the other. And I think that's what they mean by stating clearly the direction of the connection, that I cannot get from AMM to ST in 2 steps, but I can go in the other direction. So Tutzing, I can go up to P or ST directly, or AMM directly, or B directly, B to S, and T to AMM to AMB. So Tutzing can get everywhere in most 2 steps. Then we have B, can go to S or to AMB, to T, AMM, T, P, T, ST, everywhere in those two steps. Ambach. I can get to C-sharp and B, S and B, AMM and T, but I cannot get from Ambach to P or Ambach A and B to ST. I cannot do those in two, in directly or at most one stop. And then finally S. AMB, AMM, no problem. BT, no problem. But I see no way to get to Postenhofen or to Starnberg. So I count 8, 1, 2, 3, 4, 5, 6, 7, 8. That's what they have in the back of the book. I did it with the graph. I did not do it with the matrices. I just think it's easier that way. We're not done with the section, but it still has a ways to go. So we're going to break this one up into two. So I will see you in the second half.